We played with them as children, but the world of magnets isn't kid stuff. They help us travel, communicate, and fabricate. From the junkyard to outer space, to the cutting edge of medicine, these amazing forces of attraction and repulsion are everywhere. Now, magnets on Modern Marvels. For all that they do, magnets seem to be the unsung heroes of our time. Magnetism may not be as awesome as atomic energy, or as flashy as electricity. For many of us, it's merely the more user-friendly force that enables us to stick family notes on the refrigerator. But it's so much more.
We don't see the magnetism all the time is the reason we sort of forget that it's there.
But given a chance, magnets can prove quite unforgettable. At Six Flags Magic Mountain in Southern California, ride engineers turned to magnets when they wanted to design something that would shake and rattle the roller coaster world.
Six Flags wanted to build a roller coaster that went where no coaster had gone before, and that was to break the 100-mile-an-hour barrier. In order to get the speed, with conventional coaster technology, we would have had to build a lift with a chain probably close to 500 feet tall.
A more innovative solution had to be found.
So we turned to magnets and electromagnets in order to generate an acceleration of the car that would break every record that was ever known in the roller coaster world.
For maximum thrills, the ride incorporated LSM, which stands for Linear Synchronous Motors. While the technology is complex, the underlying concept is elegantly simple.
Everybody remembers from when they were kids where you had a magnet with a north pole and a south pole, and if you took another magnet and got the two north poles together, they'd repel, put the north to the south, and they would attract each other. And that's fundamentally how this technology works on the ride.
Linear synchronous motor is a means of moving an object without having to attach chains to it. But in this case, in this roller coaster, you have magnets on the car. You have electromagnets in the track. And the electromagnets can produce repulsive and attractive forces to move the car. And as soon as the car gets to the place where it's being attracted, the electromagnet changes its polarity, the current changes, and attractive force turns to a repulsive force. And you keep doing this in synchronism with the motion of the car and produce constant motion.
Banks of computers and switchers make the electromagnets shift their polarity in milliseconds.
At the end of this run of electromagnets, the car will have accelerated to an excess of 100 miles an hour. To this day, it remains in the record books as the tallest and fastest roller coaster, and we couldn't have done it without magnets and electromagnets.
Of course, you don't have to terrify yourself to see magnets in operation. They're literally everywhere, far more pervasive than we realize. Magnets are an integral component of many of the devices we use in our daily lives.
Throughout our house, throughout our car, throughout any office, there are dozens and dozens of magnets doing their work, but without being seen, out of sight, out of mind.
This invisible force that repels and attracts is in a way the cosmic glue that we harness in thousands of ways to shape and drive our world as we see fit. In fact, the world itself is a giant magnet, and everything, including us, is magnetic in some way. That's why magnets have come to play a key role in just about every kind of technology. We rely on electromagnets, magnets, and magnetized materials in the devices that transfer and retain information. They're in nearly every component of your home entertainment center. Your computer, your credit card, your phone. They're also a key feature of airport security. Magnetic fields, which are affected in the presence of iron or steel or other conducting metals, are the main feature of metal detection systems. magnets aren't just vital. They're cool. The pickup of an electric guitar is an electromagnet, which captures the waves produced by the vibrating metal strings.
People have always been fascinated with magnets. As a child, we played with magnet toys that attracted one another or repelled one another. One of the things that makes a magnet so interesting is the fact that it's perpetual. You don't have to recharge it. You don't have to add batteries to it.
I think magnetism is fascinating because of the mysteries. When you have things pulling at a distance without contact, certainly we understand when I push this hand against this hand where the forces are coming from. But when I take a North Pole and bring a North Pole close to it and they push apart, I don't see any contact. And that is always puzzling to people.
Well, a magnet is simply an object that attracts iron. It attracts some other objects that are similar to iron, like cobalt or steel, but it does not attract other things like wood, glass, plastic, copper. So it's a very selective attraction force.
There are permanent magnets, which once magnetized hold on to their magnetism forever, like the ones on your refrigerator. And there are temporary magnets, which can easily lose their magnetism. The little bar magnet attached to a CD package is temporary. It can set off the security system at the door. But if the CD is paid for, the clerk will degauss its magnet, which means he uses an electromagnet to neutralize its weak magnetic field. Unlike permanent and temporary magnets, an electromagnet is a magnet that requires electricity in order to operate. A junkyard electromagnet, for example, is used to pick up huge scraps of metal. Its magnetism can be switched on and off. Even a child can make a simple electromagnet by wrapping some copper wire around a nail and attaching the two ends of wire to a battery.
Then he touches the nail to the clips. They hang on in bunches. Jimmy has made an electromagnet.
When we make current flow through a coil, we create a magnetic field, just like in a regular magnet. But the electromagnet is different from refrigerator magnets, which never turn off.
When Jimmy disconnects one end of the wire from the dry cell, the paper clips fall off.
Electromagnetism is one of the fundamental forces of the universe, along with gravity and the atomic forces that hold matter together. Magnetism occurs because of specific properties that exist on an atomic level.
To be a magnet, material has to have each atom to be a magnet. The magnetism comes from the individual electrons that surround the nucleus of each atom.
If I put the first electron in there and it goes in this direction, and then I put the next electron in, it can go opposite to it.
Elements that configure atomically like this are not magnetic. But those atoms that don't have a cancellation because they have more electrons pointing one way than the other will give rise to magnetism. On this atomic level, a magnetic material is made up of many tiny atomic magnets with north and south poles.
And then they build up, and so eventually in a practical magnet, all the atoms are working in unison to provide the kind of force we can see.
Magnetism, the force without touch, has been a source of intrigue to humans for thousands of years. In the Western world, the ancient Greek philosopher Plato was one of the first to describe the properties of magnets. The Greeks encountered them in an area called Magnesia, from which our word magnet is derived.
In northern Greece is a source of magnetic materials, lodestones, and it was recognized 2,000 years ago and then sort of lost in the Dark Ages again.
The lodestone is found throughout the Earth and is our planet's only naturally occurring magnet. Scientists refer to it as magnetite.
It's an oxide of iron, and the basic properties of the lodestone come from its atomic structure, but How it's magnetized is still a bit of a mystery. We think there was lightning strikes hitting the rock and the magnetic fields from the lightning magnetizing the rocks.
The first practical use of a magnet made from a lodestone was the compass, a magnetic device that always pointed north. The needle was made by rubbing a piece of steel in one direction across a lodestone, thereby magnetizing it. This is a replica of a 2,000-year-old ancient Chinese instrument for determining north. The spoon-shaped magnet spun on a highly polished plate. For Europeans who began using the compass perhaps 1,000 years later, its use as a navigational tool was paramount, especially in bad weather when sun and stars were obscured. The scientific age of magnets and magnetism began in the year 1600, when William Gilbert published De Magnete and first determined that the Earth was a giant magnet. This is why compass needles, which are magnetized steel needles, swing around to point north. For the next 200 years, there was further scientific speculation, but the next big breakthrough wasn't until 1819 in Denmark.
Hans Christian Ørsted was the first to demonstrate that electric current down a wire would produce a magnetic field. He just had a compass needle near a wire. When the current went on, the compass needle turned. When the current went off, the compass needle turned back.
This was the first demonstration that magnetism could be created with electricity. The reverse was proven 1 decade later by English scientist Michael Faraday. He demonstrated that a changing magnetic field can induce an electric current. Now the world knew two of the great secrets of the universe: that magnetism in motion could produce electricity, and electricity could produce magnetism.
But it was James Maxwell, a Scottish mathematician and physicist, who put together the observations of Ørsted, Faraday, and others to put together the so-called Maxwell equations, which are the basis for all of our understanding of electromagnetism, and they are the basis of much of modern technology.
But before science and technology truly embraced the power of magnets and electromagnets, magicians and even generals recognized that they could harness the power of force without touch.
Since you cannot see the magnetic field, you can certainly move objects with hidden magnets, or they can be held in place with magnets and you don't see those. So it's quite common to use magnets in magic tricks.
In 1856, Napoleon III needed to put down a rebellion in Algeria that was being instigated by local shaman. So he sent French magician Jean-Robert Houdin to prove French magic was stronger. Houdin presented an empty box that anyone could lift. However, it had an iron bottom and could be made immovable by turning on an electromagnet hidden under the floor. With this trick, he was able to convince the shaman that through sheer willpower, he could drain even the strongest warrior's strength. This would not be the last time magnets were called out to do battle. Next, how magnets helped the Allies conquer the Nazis in World War II. The magnetic field of the Earth doesn't just help us navigate. It actually saves the planet from being destroyed by magnetic storms emanating from space. Magnets will return on Modern Marvels. The Industrial Revolution of the 19th century gave rise to the development of a growing middle class in the 20th century, creating an eager market for bold new innovations.
Consumers began to have disposable income that allowed them to buy gadgets. They began to buy household appliances, all of these various apparatuses that could or would use magnets.
After centuries of faithful, albeit limited service in compasses, magnets were finally being called up for active duty in a wide spectrum of exciting new technologies. One of the first and most revolutionary was the telegraph.
You could push a button at one place that would induce a current that would flow through a wire, and that could produce an effect somewhere else, and so you could send messages.
The telegraph made use of mankind's new understanding of the relationship between magnetism and electricity. An operator on one end could send an electric current through a wire, thereby activating on the receiving end the telegraph's electromagnet, which was set on a pivot. Its north pole was then attracted to the south pole of the permanent magnet installed in the telegraph, making the instrument move with each click made by the operator. This concept of harnessing the natural attraction between an electromagnet and a permanent magnet would be utilized in thousands of applications, including doorbells, telephones, and speakers. But by far the greatest application was in making things spin, as in electric motors, or wherever there was a shaver, a cake mixer, a washing machine, or a machine on a factory assembly line. There were permanent magnets and electromagnets making the world go round.
Magnetism is fundamental to electrical motors. And how do we drive a motor? The motor uses the attraction of unlike poles and the repulsion of like poles to help drive the armature, which is the part that rotates on a motor.
This motor has two permanent magnets called stators on the outside. The electromagnets form the rotor on the inside.
And we just keep switching north poles on as we go around the magnet.
And so this poor rotor keeps going round and round and round, trying to find a south pole to meet, but it keeps changing.
But whether or not an electrical device actually contained magnets, if it was plugged in, it ran on power. And behind that power were magnets and electromagnets.
If we're going to convert mechanical motion, a wind turbine, the falling of water, the motion of a gasoline engine, to electricity, we need a magnetic field to do that. We need generators, which fundamentally are underpinned by magnetism.
Magnets play a critical role in the generators that provide the world with electricity. As the generator turns, the magnets on it are moving past stationary copper wires. And so, by the Faraday effect, the magnets are inducing currents in the copper wires and ultimately producing electricity.
The rise of the electrical industry involved a great growth in the use of magnets. And also these things work together. As the industry grew, magnets got better. As magnets got better, the industry grew. So it was very much a symbiotic relationship between magnets and electricity.
The first big breakthrough in the manufacture of permanent magnets was in the 1930s with the creation of Alnico magnets. The name is short for an iron alloy containing 3 additional metals: aluminum, nickel, and cobalt. The 4 elements were melted together to produce a superior magnet.
Well, the Alnico magnet was better than iron, better than some of the other steel alloys, just by virtue of the fact that it was more resistant to demagnetization.
The Alnico magnets also had greater strength in a smaller package. These particular pieces have not yet been magnetized.
You need a very large magnetic field to magnetize them adequately. So what you want to do is have an electromagnet with a large current.
The current will come from the magnetizer. It contains a bank of capacitors which store electricity. The material is placed into this container, which is an electromagnet, connected to the magnetizer. When a button is pushed, a jolt of electricity, perhaps 100 volts, is delivered in a millisecond. And the part has been magnetized. By far the most dramatic use of Alnico magnets occurred during World War II. The Axis struck the first blow in what, to a very real extent, turned into a magnet war. The Nazis had used compasses with steel needles at the beginning of the war to set off underwater mines, which sank a number of British ships.
The German magnetic mines were settled so that the compass needle was sitting there just feeling the Earth's magnetic field.
When a steel ship passed over these mines, the needle would rotate, triggering the electrical system to ignite the bomb.
You have been reading in the newspapers of this latest abomination of German savagery.
The Allies quickly turned to their textbooks on magnetism to address the problem.
The first newsreel pictures of that famous bomber, the Wellington, being used for the detection of magnetic mines are now released. By means of a generator and the coil in that huge ring, an electromagnetic field can be set up which has the same effect on a magnetic mine as that of a passing ship. To detonate the mines, the aircraft flies over the sea at 60 feet or less. Tricky and dangerous work.
The war turned when the Allies used Alnico magnets to create magnetic fields in specialized vacuum tubes called magnetrons. These generated high-power microwaves for Allied radar systems. As the Axis powers lacked the raw materials of Alnico, the magnetron and radar in the Allies' arsenal struck a crippling blow to the Nazis' Navy and Luftwaffe.
It allowed the Allies to come victorious from the war because they were able to pinpoint the location of these airplanes and bring many of them down, which was critical in winning the war.
Today, this microwave technology is also used in our household microwave ovens to defeat hunger. But the hunger for information would be the driving force in the post-war prosperity. Next, magnets make the information age more attractive, functioning as essential components in communication technology. The magnet in the motor of a laptop is so powerful, it makes the hard drive spin at a rate of 5,400 revolutions per minute. Magnets will return on Modern Marvels. As America shifted to a peacetime economy after World War II, industry and technology worked hand in hand to lead the country to a more prosperous future. The second half of the century would be defined as the communications and information era, and magnets let their versatile capabilities do the talking. In the post-war years, television became a reality after decades of development. The deflection of the electron beams that essentially paint the picture on the television screen is accomplished using electromagnetic fields. Years later, when VCRs and videotape became ubiquitous partners to the TV industry, magnets and magnetic materials made these technologies possible as well. The VCR's motor, like any electric motor, consists of permanent magnets and an electromagnet. The tape head is a magnet that takes in the signal, and the tape itself is called magnetic tape, mylar, coated with millions of tiny magnets, which serve as the memory units to store information.
A North Pole up gives one measure of something. A North Pole down gives another measure of things. And once we can say this is yes and this is no, then we can build a memory device out of it.
In the 1950s, scientists realized this very concept, that magnets are not just devices with the power to attract and repel. They can also be repositories of data. Data that is transferred as electromagnetic signals.
When the electrical signals go in, there's a recording head which actually records a north or a south onto the magnetic tape. It's equivalent to a 0 or a 1.
Zeros and ones are the ways computers break down information. This translates into norths and souths of the tiny bar magnets embedded in magnetic tape and disks. This ability is what made the computer age possible. This same technology also gave us the credit card, with its strip of magnetic tape.
Embedded in that are many thousands and thousands of very, very tiny magnets that are magnetized in certain patterns, north and south poles pointing in different directions, that will tell you what your account number is in your credit card or your bank account.
As technology was finding new and more useful applications for magnets, the magnetic industry continued developing new materials. In the 1950s, ferrites, a new kind of iron oxide alloy, was introduced that provided the first step in downsizing motors and electrical devices. Because of their lower cost, ferrites were widely adapted, but most importantly, their magnetic properties allowed for magnets that were more compact than those previously made with Alnico.
The ferrite magnets allowed motors to be made in a smaller diameter, shorter length, and really the application fitted itself very well for the automobile industry. Now you could have seat positioner motors, for example, that fit very nicely beneath the passenger seat and window lift motors that were now small enough to fit very nicely into the door of an automobile.
In Elizabethtown, Kentucky, this factory has been making ferrite magnets for nearly half a century. Gareth Mycock is Chief Operating Officer of the VAC Corporation's facility here.
This is iron oxide, a raw material delivered to the plant for the production of hard ferrite magnets.
The powdered iron oxide is loaded into giant drums, mixed with other compounds, and milled into an even finer powder. When this process is done, the materials have to be heated.
This is a large tubular furnace where the pre-mixed raw materials react together and form into a pellet-sized material. Reaction takes place at about 2200 degrees Fahrenheit.
In the presence of a magnetic field, the robotic hydraulic press then compresses the material into the desired shape. It's only held together mechanically at this point. If dropped, it would simply fall apart. Next, the parts are loaded into a large gas-fired kiln and heated, again at 2200 degrees Fahrenheit. This causes the molecules to bond together, making the finished piece uniform and hardened. After some grinding and polishing, the parts are ready to be magnetized. Ferrite magnets are still widely used today, whenever great strength isn't required and keeping costs down is a factor. In fact, your refrigerator magnet is probably a ferrite. But a new generation of magnets has taken center stage.
In the 70s and 80s, the rare earth magnets came along. They were based on this collection of elements in the periodic table called the rare earths.
The rare earths are alloys of rare earth metals, most commonly samarium cobalt and neodymium iron boron. These packed a lot of power into a tiny package, 100 times stronger than the early iron and steel magnets. From this chart, we can gauge the comparative strengths of ferrites, samarium cobalt, and neodymium iron boron magnets. Rare earth magnets, as much as transistors, paved the way for the age of miniaturization. But it didn't come cheap.
We pay for more expensive material when the application absolutely requires it.
While 100 times more expensive than a ferrite magnet, there was no question some applications demanded miniaturization at any cost. For example, a hearing aid that previously hooked onto the back of the ear could now fit entirely in the ear.
If we're going into hearing aids, we want a small hearing aid. We are not going to stick in a ferrite. We're going to use a very high-strength magnetic material.
This process of downsizing was responsible for tiny earphones for the portable audio devices and palm-sized cell phones. But perhaps the most vital innovation due to rare earth magnets was the dawn of the laptop.
The consumer doesn't know that the magnet was one of the driving forces that allowed for the miniaturization of computers. And the fact that that magnet can be made stronger and stronger and stronger while it's getting smaller.
The rare earth magnets facilitated the creation of the miniature disk drives inside laptops.
You simply couldn't have most of the consumer-oriented apparatuses that you have today if you didn't have the magnet technology that exists today.
Rare earth magnets also made possible luxury car features previously unheard of. With magnets operating the dozens of tiny motors for all the power options now available. Ultimately, it is the consumer, demanding products that are smaller, more convenient, and more efficient, who is the driving force behind the numbers and kinds of magnets in use today. But it is the scientists and think tanks who drive the creation of supermagnets. Next, the development of superpowered magnets helps big science probe the nature of matter. Scientists believe that pigeons, sea turtles, and bees navigate by aligning their own internal magnetic fields with that of the Earth. Magnets will return on Modern Marvels. In Tallahassee, Florida, on the campus of Florida State University, is the National High Magnetic Field Laboratory. It is here where you'll find the world's biggest and most powerful magnet. Rated at 45 Tesla, meaning the magnetic field it generates is 1,000,000 times greater than that of the Earth. It is a powerful research tool for every field of scientific endeavor.
Well, the mission of the laboratory, the primary mission, is to conduct science in very high magnetic fields.
The main reason that we seek out these very, very high fields are much the same reason we might measure things at very high temperatures or very low temperatures, very extreme conditions. When you move to new areas, just like Captain Kirk and Captain Picard, when you go where no one has gone before, you are bound to learn some new things.
The magnetic field of 45 Tesla is the result of combining the power of a giant electromagnet and a nitrogen and helium-cooled superconducting magnet. The magnet is so powerful, it can actually levitate materials that you wouldn't expect to react to magnetic fields. It's able to do this because of the fact that on an atomic level, everything demonstrates some kind of reaction to a magnet. An element like iron will be attracted to it, which means it's ferromagnetic. Most elements are repulsed, meaning they are diamagnetic, and that force is very weak.
How do we actually see this diamagnetic force in real life? Well, we can use a very, very large electromagnet, like similar to the one in back of us.
Perhaps the most dramatic demonstration of this kind of magnet's power is what it can do with an ordinary frog.
Frogs are 90% water, and water is diamagnetic. And let's imagine what happens when we bring a frog near the center of a high magnetic field region. When we do this, the diamagnetic force on the frog gets larger and larger.
It may look like the frog is in water, but it's not. The intensity of the magnetic field being generated is canceling out the force of gravity. The frog is levitating in air. As remarkable as this may seem, this is a mere sideshow for the scientists who come to NHMFL. A lot of what is known as big science comes out of this kind of research. But one of the biggest breakthroughs, the development of the MRI, magnetic resonance imaging, happened while science was, in a manner of speaking, looking the other way. In the 1940s, it was discovered that the magnetic fields of every atom could be followed and actually seen if they were stimulated by another set of magnetic fields. In this case, radio signals, which are actually electromagnetic waves. Decades later, an intellectual leap was made, not by the physics community, but by the medical world.
We were looking for the prospect that maybe we could use it to build a body scanner that would be sensitive to different tissues. We were delighted when we were able to show that this magnetic signal from the atomic nucleus would indeed differentiate rather dramatically cancer tissue from healthy tissue.
After years of research and experimentation, Dr. Raymond Damadian and his colleagues invented the MRI. The tiny magnets in the nuclei of our atoms, which scientists call magnetic moments, can now be seen.
By putting the human body in a large magnet, we cause those nuclear magnets to line up in the main magnetic field. The minute we apply that alternating magnetic field, we'll cause those nuclear magnets to tip. And when they tip, we can detect the signal. When we turn off the tipping magnetic field, those nuclear moments will relax back to their original orientation in the magnetic field and induce a voltage in the detector coil that will be the signal from which we'll make the picture.
The science of using high magnetic fields to probe the nature of matter began in the 1940s at MIT, under the guidance of Dr. Francis Bitter. Dr. Carolyn Ross is continuing that tradition at MIT, using a magnet that generates high fields in her quest to find a new material that will make computers function better.
The next big thing that's coming along is called MRAM, that's Magnetic Random Access Memory. And what that is a magnetic chip that you can put in your computer, and it acts like the memory chips we have now, except that when you turn the computer off, the information stays there. And so when you turn the computer back on, all the information is still there and the computer comes on immediately without having to wait for it to boot up.
Just as an MRI can probe the human body, this magnet generates fields high enough to probe the magnetic characteristics of materials that might be suitable to store the MRAM data.
This machine has a couple of big magnets. These are electromagnets. So we pass a big current through some coils, and that produces a magnetic field which we use to influence the sample that's sitting right in the middle there.
It's a long process of trial and error, but once MRAM becomes a reality, it will have been worth the effort, and ultimately, another technological triumph for magnets and magnetism. Nuclear physicists are also using magnets to probe matter, but without a specific application in mind. As giant electromagnets guide the path of nuclear particles traveling at nearly the speed of light in atom smashers, scientists are attempting to unlock the secrets of the universe. Next, magnets are being tested to solve gridlock and even take us planet hopping. The big magnet at the NHMFL in Tallahassee consumes as much power as 4,000 homes, with a monthly power bill to match of about $180,000. Magnets will return on Modern Marvels. While magnets have been known and utilized by man for some 2,000 years, their widespread application is just over a century old. But based on their stunning yet relatively short track record, it's reasonable to expect that magnets will help us create our future in a number of exciting ways. As new magnet-based technology is invented, mass production waits in the wings. One-of-a-kind designs are tested and created, often in boutique-type factories.
We're a different sort of magnet company. We don't make millions of anything. In fact, sometimes we'll only make one of something. And that may be all that's ever required. We make magnets that go into some of the atom smashers. We make magnets that will go into space, perhaps to adjust the mirror of the Hubble telescope. We make magnets for medical applications. Everything we do is custom.
Designs and magnetic field calculations are first worked out on computers.
We can not only visualize but also calculate the magnetic field and how it behaves in a particular system.
More often than not, the material of choice is a rare earth alloy. The specifications are so precise, these bars come with paperwork attesting to their pedigree. After they're put through several stages of proprietary processes, they are ready to be assembled. Sometimes many magnets will be configured into one assembly.
What we have here is an assembly that's being built. There are approximately 100 different magnets. They're all magnetized in different ways and different orientations.
Ultimately, this device will be used in an experimental and revolutionary type of surgery, much like this simulation, in which these magnets will guide catheters that are inserted inside a human body. Scientists and industrial designers are also experimenting with new systems in which the attractive and repulsive properties of magnets will facilitate movement without friction. This concept is already a reality in magnetic couplings. Remarkably, these can transfer torque from one component to another without touching at all. Magnetic bearings are next up on the horizon.
If we have an old turbine that has a bearing, there's friction and there's wear and there's failure associated with those. A magnetic bearing has no touching parts. Therefore, there's no wear.
Similar technology will also help us to travel in bold and innovative ways. Maglev trains are one mode being tested in Japan, Germany, and here in the US. Maglev, or magnetic levitation, is simply the practical application of the basic magnetic concept of like poles repelling each other. It's what happens when either two norths or two souths face one another. But magnetic levitation always occurs vertically, as demonstrated by these two rings. The top ring is merely steadied by the pencil in the middle. This toy levitron, steadied by gyroscopic action, is doing the same thing. Because there's no contact or friction, the maglev train requires an equally unique system to make it move.
Now, of course, it's not touching the track anymore, and you can't just rotate axles and wheels to move the thing, so you have to move it again by magnetic forces, and you use the same kind of techniques that you use in a motor.
Remember the Superman ride? It's the same idea.
This is, for example, another application of the linear synchronous motor. If you synchronize the changing of the poles with the motion of the train, you can keep the forces going.
The railways aren't the only transportation systems that can benefit from innovative magnet technology. In California, civic engineers are testing a concept that would turn a line of automobiles on the freeway into cars of a magnetic train. Magnets that are spaced apart and embedded along a special lane in the highway, as well as magnets under the cars themselves, would guide vehicles along, keeping traffic flowing steadily and freeing the drivers to relax. With an eye toward traveling beyond the Earth, scientists and engineers at NASA are exploring ways in which magnet technology can facilitate space travel.
One of the things that we're investigating that deals with the use of electromagnetic energy is a launch assist system. And this is a ground-based electromagnetic rail with levitation coils and a linear motor that provides thrust to give a launch vehicle the initial velocity from dead stop up to, let's say, 400 to 600 miles an hour. We have no contact with the ground due to the levitation, and then the linear motor provides the acceleration and the propulsion in the forward direction.
A key advantage to this system is that a tremendous amount of fuel that would normally be used to launch the aircraft through Earth's gravitational pull could instead be used to propel a ship further into space. Perhaps the ultimate use of magnet technology would be to facilitate interplanetary manned space travel. Revolutionary plasma fuel systems could accomplish that. And magnetism would play a key role. Plasma are superheated gases like those found on the sun. Their key advantage is that they are much lighter than conventional rocket fuel, so less fuel would be needed to travel deeper into space.
The role that magnets might play in future propulsion concepts lies in the ability of magnetic fields to contain high-temperature plasmas.
The plasma must be kept away from the walls of the propulsion system so they don't burn up. The engineers believe magnetic fields are the only force capable of directing the plasma through the reaction chambers. If NASA's theories are correct, the results would be nothing short of revolutionary.
This concept would eventually lead to enabling humans to go anywhere in the solar system, anytime they want to go, and at reasonable cost.
So, there you have it. The wonder of magnets. Who among us would hereafter scoff at the lowly refrigerator note holder, knowing how vital magnets have been in virtually every aspect of our lives? And also knowing that magnets could play a role in accomplishing what mankind has dreamed of since time began. How fitting that a technology that helped Columbus find his way to America could help future astronauts reach the heavens.